In the burette, we are going to have potassium dichromate. Potassium dichromate is an orange crystalline solid. And so, of course, the solutions that you make of potassium dichromate are bright orange. And in your samples, you're going to have samples of Fe plus 2. Fe plus 2. So the first redox reaction that we're going to study is the one you're doing in your lab. Fe plus 2 plus Cr2O7 minus 2 to give me Fe plus 3 plus chromium plus 3. And at the end of today, somebody remind me to talk about the date for the exam, please. At the end of today's class. Don't let me forget. So oxidation is losing electrons. Oxidation is losing electrons. And reduction is gaining electrons. Leo the lion says GER. Or oil rig. Yeah, I know you're an oil rig kind of guy, but I'm good. Just saying, you choose your own, and you have your own reasons, and that's it. And that's all we talk. So, but don't mix them up. Make sure that you always remember oil rig or Leo the lion says GER. Don't mix them up. So, I like to think about the number line. Believe it or not, at least in the beginning, you know, there's no shame in it. Just write up that number line, like when you were a little kid. There's no shame in it. So if you go in the positive direction for an oxidation number, the oxidation number for an item, if you go in the positive direction, that's an oxidation. If you go in the negative direction, that's a reduction. Don't forget that your gain and loss is a negative thing. And that is an issue because that confuses people. You are gaining and losing negative things. So when you gain electrons, you're increasing your negativity. That's a reduction. It's a definition of reduction, the gain of electrons. Is that fair? That's what drives people to drink when it comes to redox. Because you're gaining, and it's the truth, you're gaining and losing negative things. Because everybody wants to say gain. Oh yeah, right, well that would be positive. But your gaining is negative. You get that? So therefore, thinking in those terms, if I see that iron goes from plus 2 to plus 3, that is unequivocally a loss of an electron. And what is that? An oxidation. Absolutely. So iron has undergone the oxidation. That absolutely means, absolutely, without any shadow of a doubt, that means that dichromate underwent what? The reduction. Is that fair? Okay. So now, let's do some talking about oxidation numbers. Coming soon to a 1045 lab exam near you.
So, I just want to make sure.
Yep, go ahead.
Oxidation is when you gain electrons.
No, reduction is when you're gaining electrons.
So oxidation is when you lose it.
Leo the lion says GER. Losing electrons is oxidation.
Oh,
Gaining electrons is reduction.
okay.
I told you. That's what makes people crazy. All right, numero uno about oxidation numbers. It's something that you've already heard about a million times, and that is elements in their oxidation state, in their elemental state. Oxidation state, 0. Uncombined, of course they are. Of course they are. So things like H2, O2, N2, Fe solid, chromium solid, oxidation state, 0. Are we comfortable with that? So ions have their oxidation number, they wear it in the upper right hand corner, their oxidation numbers. So this guy is a +3, that guy is a +3, that guy is a +2. Now let's talk about that chromium. Let's talk about oxidation numbers in polyatomic ions. Oxidation number in polyatomics. There's a couple of ways of doing it, and there's no better way than to just go ahead and practice. As many as possible, as fast as possible. So here we go. This is called, give the oxidation number of the element that is underlined. The element that is underlined. In polyatomic ions, you're going to take a guess. You're going to guess that oxygen is a -2. Because 85 times out of 100, you'll be right. Did you notice I said 85 and not 99? 85 times out of 100, you'll be right. Why is that true about oxygen? Because oxygen has other oxidation numbers. How do you feel about oxidation number for that guy? What's his oxidation number? 0, an element in its elemental state. What's this called? No, that's just regular oxide. I just wrote a -2 up here. What is peroxide? O2 minus 2 is peroxide. Yeah. Is that right? Okay. And how about this one? What is the oxidation number of oxygen here? 0. What's the oxidation of oxygen here? -2. Hey, what's the oxidation number of oxygen in peroxide? -1. What's the oxidation number of oxygen here? No, you know it can't be -2. What's potassium? Is potassium fixed or variable? Fixed. Potassium is fixed. Come on now. What does it absolutely mean about the oxidation number of that oxygen?
1.
What? Not my fault. I swear. It's called a superoxide. I'm not making this up. I make stuff up, okay, but not that. I swear, it's not my fault. A superoxide. Okay? So it's not that uncommon. Superoxides are actually pretty common. Potassium superoxide is actually the most common of the superoxides. And it has a really interesting property. When it's a solid, and when you put it in a small container, and you run humidity across it, it produces oxygen. It decomposes spontaneously and produces oxygen. How can I make this work for me? How about if I put it in a small box? Where would it be important for me to have something such as this?
Airplane?
Somewhere where I could run out of oxygen, but I would be perspiring.
Space station?
Under reduced oxygen conditions, what occupation might put that to use?
Submarines.
Astronauts, airplanes.
And here on the planet? How about firefighters? Under reduced oxygen conditions, you can have a cartridge that by you just being inside of that container releases oxygen for a short period of time. So actually, it's not that uncommon. And yeah, you're right. Oxygen can have a bunch of different oxidation numbers. Remember what we said. The fixed oxidation numbers on the periodic table are very few. 1A metals, 2A metals, and we fixed a few others on the periodic table. Cadmium, aluminum, silver, right? That means that everything else on the periodic table is variable, so it shouldn't surprise you that oxygen turned up -2, -1, and -1/2. Who knew? We good? When it comes to oxidation numbers, you are going to guess that oxygen is a -2 because 85 times out of 100 it is. Most of the oxygen you encounter is -2, but not all of it, because I know about peroxides and now I know about superoxides. You good? So we're going to guess oxygen at -2, and then we're going to figure out the oxidation number of the other element in the polyatomics. And this is an exercise that you need to be able to do very, very quickly in your head. So here we go. I assume oxygen is a -2. I'm going to guess. If I have to guess at an oxygen, I'm going to guess it's a -2. And sulfate has 4 of those guys. So how many negatives do I have on the table? Because that's a 4. 8. So I'm at -8 from the oxygen that brought -8 to the table. You know, apparently, that sulfur neutralized all of them, but he left 2 out. So he had to have been
A 6.
not just a 6, a +6. You remember oxidation numbers carry a sign and you have to say it. You have to say that plus. +6, +6, +3, +4, -2, whatever it is, you have to say the sign. So let's pick up a little speed. I have to guess a -2. There's 3 of them, so there's -6 on the table. That phosphorus left 2 out, so he had to have been +4. So what's this? 8, 1, +7. How about this one? -2, 8, 1, +7, right? Okay. So tell me, any questions on doing that? Can you do that always? Yeah? How about this? ClO2 -1. How about ASO4 -3? CO4 -3. -2, 4, left 1 out, +3. -2, 8, left 3 out, +5. -2, 8, 3 out, +5. Yeah? Okay. All right, you can do it. You can do it. Okay. So, talk to me a little bit about that chromium. I know how it ended up. I know how it ended up. But I don't see it. Tell me.
How would you do like the superoxide ones? The same way?
Yeah, we kind of did it because we know that this was fixed at +1.
Okay.
If that is fixed at +1, and that's a non-negotiable, then this had to have been a -1/2, which is crazy, but it's true.
But like we wouldn't put the -2 for the oxygen, or no?
No, you can't. It's a -1/2.
Okay.
And how do I know that? Because this is fixed.
Okay.
That's never going to be anything other than +1. And that's the thing about oxidation numbers. When they tell you to figure one out, it means they assume you know one of them. That's why that step is important. Because you're going to assume that oxygen is a -2 in the polyatomics, which it is. We good?
Yeah.
Okay.
Thank you.
Item number 3. Item number 3. Item number 3 is about hydrogen. And hydrogen. With the metals, it picks up a -1 charge. Okay? No, we're getting there. Hydrogen with the metals, it picks up a -1 charge. And hydrogen with the non-metals, it becomes a +1 charge. What's the oxidation number for nitrogen and ammonium? nitrogen is a non-metal. Is that correct? That means that hydrogen is adopting a what? A positive. So that means that I have a +4 on the table, right? That means that that nitrogen neutralized all of those, but left one out. He had to have been only -3. We good? Right. So I think you're ready. I think you can tell me what the oxidation number of chromium is in dichromate. Because I'm guessing oxygen is a -2, and there are 7. That means that this is -14 on the table. And apparently, these 2 chromiums neutralized all of them, but they left 2 out, so they must have been working a +12. Together, right? So the oxidation number for chromium in dichromate is, you betcha. There's your reduction. It went from +6, it went from +6 in that direction to +3. There's your reduction. The oxidation number that goes down, that item is undergoing a reduction. Remember, the number went down. It was reduced. That's the easy way to remember it. When the oxidation number goes down, that item is reduced. So,
Why isn't it +12?
well, do this one for me. This is -2. On the table is -8. He left 2 out, so that must have been +6. But you know, that's by himself, right? The thing is, through no fault of your own, dichromate is Cr2O7. It's not my fault either. So whoever is neutralizing these 14, whoever it was, it left 2 out. So they were working a +12. The thing is that there's 2 of them doing that. So the oxidation number for chromium in dichromate is +6. We are good? Is that fine? So now I clearly see the oxidation and the reduction. Is that true? Sometimes the question of oxidation and reduction comes in like this. And they say, hey, give me the oxidation number of all the elements of the following compound. This exercise is exactly the same as the one we just did. In other words, I want you to do this problem exactly like we just did the other 10 that we just did. That means that you need to separate the items into the 2 ions. Why? Because if you try to do it together, it takes too long and it gets very confusing. So when someone tells you, give me the oxidation number of all of these, you say, wait, what is this really? This is sodium +1, isn't it? And what's his partner? Sulfate. Ah, I know how to do this. Fixed, +1. And now, sulfate, -2, -8, left 2 out, +6. So now I know all of them. But I need you to separate them out and do the polyatomic by itself like we just did. Compartmentalize it. So now I know this one is fixed at +1. Now I know that's a +6, and that was going to be a -2. So now I know all of them. But because I separated them. How about this guy? What are you going to do? Separated. What is this really? PV what? Yeah, PV +2. Gotcha. Gotcha. PV +2. And who's his partner? Phosphate, you know. Phosphate, you know, phosphate. PO4 minus 3. So now, just go ahead and do it. Minus 2, 8 on the table, left 3 out, plus 5. You don't need me at all. Separate them out. How are you going to separate this one? What's that really? Oh, yeah. Yeah. At plus 1. Yeah. Hydrogen with a bunch of nonmetals. A plus 1. Done. I knew that. You have it written down. And who's his partner? Sulfate. I know how to do this. Assume a minus 2, minus 8. 2 on the table, so plus 6. Done. We good? Here's a warning to other methods of doing this problem. It is possible to do this with a little equation, and you solve for x. When you set it up like that, you take too long, and if you solve for x wrong, you're going to get it wrong, so you're blowing it even at the start. Let me show you what I mean. The overall charge for an ion, of course it's the contribution of all the individual elements in the polyatomic. So when you do this with a little algebraic formula, what you say is, look, all of those guys together make a minus 2. And I already know that the oxygen is going to be minus 2. And there's 7 of them. So just state it as a mathematical truth and solve for x. Oxidation number of all the elements. Oxidation number of all the elements. In what is that? What's that called? Ionic covalent or an acid? Ionic, fixed or variable? Variable. So it's called iron 3. What is that? Chlorite. I'm sorry. Is that T as in Thomas or D as in David? T as in Thomas, chlorite. And it has to be iron 3 chlorite. Is it ferric or ferrous? Ferric. Because the higher one is the Ich, the lower one is the O. So, hey, I already know what the iron is. It's a plus 3. So, who's everybody else? What's that? Ah, it's chlorite. So now we're back to normal. Each oxygen, I guess, a minus 2. And there's 2 on the table, so how many do I have in total? Minus 4. That chlorine neutralized all of them, left 1 out. He had to have been plus 3. Or you can do minus 1 equals the Cl plus 2 times minus 2. Damn the remedial math, but there it is. Damn the remedial math, but there it is. If you want to go that route, that's okay. But just be fast about it and make sure you don't do some numbskull creative thing with the math that causes you to do that wrong. Like claim, for example, that this is our chromium is going to be a plus 12. So please be careful with that. Be good? This is called, and reactions like this are called the skeleton equations. The skeleton equations. And we did that because to make your life easy, we removed spectator ions. To make your life easy, we removed spectator ions. Like which one? Like that one. Spectator ion. Removed. To make your life easier. We removed it from the statement of the equation that represents that redox reaction. But in fact, you know we didn't make it disappear. We can't do that. The potassium dichromate, for those of you that have already done the experiment, was in a bottle. It was in a bottle in the back of the lab. It was a solid, a very beautiful orange crystalline solid. Right? You know, it weighs 294.2 grams per mole, and that includes about 80 grams of potassium. because I can't pretend the potassium isn't there. I did remove it in the skeleton equation to make your life easier so you wouldn't have to deal with an item that doesn't undergo a change in oxidation, so it's not part of the redox, and it's going to be in the way of you understanding what redox is. So the skeleton equations have spectator ions removed. Is that fair? Okay. In your labs, you're going to apply the concept of normality and the equivalent weight and the concept of the equivalence to redox reactions. The modification is the following. In acids and bases, what was the equivalent? For acids, it was the H+. For bases, it was the hydroxide. Right. You know what the equivalent is in redox? The electron. In redox, the equivalent is the electron. I earlier defined the equivalent as the business end of the molecule. And that's very true. What makes an acid an acid?
Hydrogen.
Its ability to cough up a proton. What makes a base? Its ability to pick it up. So of course these guys are going to act as bases, the hydroxides are. And the acids are going to be the proton donors, and these bases are going to be the proton acceptors. In redox, what's the currency? What are we trading in? Electrons. Those are your equivalents. So now, when you do equivalent weight in redox, is the formula weight for the whole compound. And please underline and highlight the whole compound divided by the number of electrons per mole. The number of electrons per mole. Is that fair? Okay, let's calculate the equivalent weight of iron and the equivalent weight of dichromate. Equivalent weights are always the same. The formula weight divided by the number of equivalents. The formula weight divided by the number of equivalents. So Cr2O7 minus 2. It is not your fault, but this had 2 potassiums at +1. And the formula weight for the whole compound is 294.2. What are the units of molecular weight? Grams per mole. And iron, since we're talking about iron, how much does iron weigh? 55, 56 grams per mole divided by the number of electrons. Divided by the number of electrons. How many electrons was the oxidation of iron involved in? Iron took a trip from +2 to +3. Its oxidation number went up in the direction of oxidation. So it was oxidized by the gain or loss? Loss of chromium in dichromate. Chromium in dichromate. The reduction of chromium in dichromate involved how many electrons? 3 electrons per chromium, right? Nah. And through no fault of your own, in dichromate, there are 2 chromiums buying that little ticket from 6 to 3, right? Say yes.
Yes.
So the total number of electrons per mole of dichromate is? I thought I was a little overwhelmed with that 6, so let's do it again. The reduction of dichromate involved how many electrons? 3 per chromium, right? Because chromium went from +6 to +3. It, gain or loss? Say gain. Gain. It went from +6 to where? +3. It was reduced by the gain of things that are negative. Right? Each chromium gained how many electrons? 3. To go from 6 to 3. But dichromate has 2, right? So per mole of dichromate, how many electrons are involved in the reduction? 6. Because each chromium +6 took 3 electrons to become chromium +3. How many chromiums are in dichromate? 2. Each chromium, through no fault of your own, gained 3 electrons. So for the entire mole of dichromate, how many electrons were involved in the procedure? 6. Because through no fault of your own, dichromate has 2 of them, making that little trip. And that is the equivalent weighted redox. We good? Don't worry, it gets worse. Hold on, I can't hear you.
Let's say the chromate didn't have 2, meaning the oxidation.
Okay, then let's say it wasn't chromate, because if it weren't for gravity, time, and genetics, I'd be a supermodel. And so, let's not say that, because I can't. Let's do this. CRO4 minus 2. It's 3. My only enemies in life are genetics, time, and what else did I say?
Gravity.
Gravity. All right. So, suppose that the chromium in the chromate, suppose that chromium and chromate ends up in a redox situation where he finds himself as +4 at the other end. Tell me, was that an oxidation or a reduction? Let's practice. Crap, this is one of those stupid things where I have to figure it out. So -2 times 4 minus 8, left 2 out, +6. Ah! He went from +6 to +4. What is that? A reduction. So he must have gained 2 electrons. Is that fair?
Yes.
So tell me something. If the entire reagent was Na2CrO4, what would the equivalent weight be like?
What?
The equivalent weight would be like the entire formula weight for the whole compound divided by how many electrons? How many electrons were involved in this transaction?
2.
Each chromium went from +6 to +4. So he had to have gained 2 electrons, right? Per chromium. And how many chromiums are in this chromate?
1.
Only 1. So, only 2. For the same exact reason.
So then if chromium would have been 2, it would have been 4? Like dichromium, it would have been...
Hold on. If I can say it wrong. Do it again here. What's the oxidation number of bromine in the elemental state?
0.
0. So what was he over there? So 6 minus 1 plus 5. Plus 5, right? Not good, you guys are getting fast at it. So it went from +5 to 0. Right? It went from +5 to 0. Wow. +5 to 0. There's no shame in it. You write that number line. There's no shame in it. How many electrons electrons were required? That's a massive reduction. 5 electrons. That's a crap load of electrons in a single mole. But there it is, nevertheless. Bromine went from +5 to 0. Not your fault. How many electrons were required?
5.
Per bromine, right? So, say for example, what if it had been potassium bromate? What if it would have been potassium bromate? What's the equivalent weight? The equivalent weight will be equal to the formula weight for the whole compound divided by
5.
5. 1, 2, 3, 4, 5. 1, 2, 3 electrons. Right? The formula weight includes all of the atoms, even the spectators. And the denominator will be the number of electrons in the oxidation or reduction per mole of the compound. You had something a minute ago.
Yeah, I don't understand why then it was +6 for the.
Yeah, how did it, yeah.
How this +6 came about?
Yeah, like why wasn't it +3?
Here, do it the same way you did it here. Dichromic. The oxygen, you guess what? -2. There's 7 minus 14. There's 2 out. So these guys were working up +12. But there's 2 of them doing that job. So each of them had to have been what? +6. That's their oxidation number.
But here,
And together they make a 12.
But then it ends up as.
And it ends up at +3. That's not my fault.
So that's.
That is not my fault. I had nothing to do with that. It could have ended up as a +4 or +6. I don't know. Chromium has a whole truckload of oxidation numbers.
But then wouldn't that.
Silence! Silence!
Wouldn't that mean that he gained 3 electrons for each chromium?
Oh, that's what it says right here. Each chromium gains 6 electrons to become chromium +3. I agree. And so when you calculate the formula weight, you include the potassium, and that's 294. But what do you divide it by? The number of electrons per mole of the compound, right? And how many chromiums, guys, straighten this out. How many moles of chromium are in dichromate? So the total number of electrons is? Not my fault. So here you went. A single chromium +6 went to +4. How many electrons is that?
2.
And there's only 1 chromium there, so when I do that formula weight, I'm going to divide it by what? 2. By 2. And here's bromine going from +5 to 0. That was 5 electrons, but potassium bromate has only 1 bromine, so the total will be 5. If it had 2 bromines, what are you going to put down here? 10, because it's per mole. You good? The rest of the conversation about normality is the same. Fortunately, it is exactly the same. And you do exactly what you did in acid base. It always starts out with equivalence of one reagent equals equivalence of the other reagent. So equivalence of iron equals equivalence of dichromate. And the rest of it, same business as usual. Grams over equivalent weight equals normality times volume. Because this part is in the burette. That's that orange stuff. And this is what you're analyzing. This is the pre-titration of your iron sample. Those are the 3 titrations of your iron sample. Everything else is business as usual. Jaron, yeah, I had a cousin named Jaron. No. What's a Jaron? Come on. That never mean you English. Jaron.
Oh, is that the one with the ING?
There you go. There you go. The part of speech that ends in ing is called a gerund.
Half the English and chemistry.
But that's how we roll. That's how we do it. That's how we do it. We put it right across the curriculum, and when you least expect it, bam, ground. Exactly. Exactly. Math classes, chemistry classes, that's how we do it. Listen, you're paying good money for this. I swear to God, there's a point to this. I swear. Sometimes they're going to ask you questions, okay? And the questions can be as simple as, which species, in the synonym for this one is ion, or atom. Which species was oxidized? Which species was reduced? And I think that we've gone far enough that we can comfortably answer both of those questions. What was oxidized? What was oxidized? Iron, right? Which iron? Because I see two of them. What was oxidized? The iron? Plus 2. And you have to be specific, or they're going to mark it wrong on the lab exams. If you answer just iron to this question, they're going to mark the whole thing wrong. Because there's 2 irons, you have to say which one. It was the iron plus 2 that was oxidized to plus 3. That's where the language comes in. I wasn't kidding about the language. I swear to God there was a point to it. What was reduced? So a better answer, a more specific answer to that question would be the chromium plus 6 in dichromate. And if I wanted to be really specific, I would finish that sentence saying that the chromium plus 6 in dichromate was reduced to plus 3 by the gain of 3 electrons per chromium atom. And it doesn't get more specific than that. Because that tells the whole story though, right? That tells the whole story. Now I have to ask you a question before we go into the gerund. Are you okay with these two?